All right, we're going to talk about threshold encryption, and we talked about multi-signatures from the perspective of being the M out of N solutions in a matrix. But this is not actually the multi-signature algorithm that is implemented in Bitcoin today. In Bitcoin today, it is always all signers that are on a multi-signature have to sign it. And they have a fixed amount of space for different signers to sign, which means you can have between 2 and 15 signers. Now, for the multi-signature to actually work in Bitcoin, it requires that you actually have all of these people participate at the same point in time. They all have to be online. And there are other multi-signature wallets for other things like Ethereum that work in different fashions, but these are not actually built into the chain itself. It means that you have a multi-signature that is going to release a signature that is then going to sign it, and you have to trust that your third party that you've given over this kind of a signature to is actually trustworthy to actually do this. So these are off-chain multi-signatures. Now, in an ideal world, what we would do is we would have an online signature. And that online signature would allow things to happen in our contracts to implement it so it could be automated. With offline signatures, then all you've done is you've moved your requirement that people be online all at the same time from on the chain to you've stepped it back to some other third party that you now have to trust. So when we talk about threshold encryption, the value of the threshold encryption is a number of things. The first one is that when we get done with generating a key pair, the public portion of the key pair is a big number that can be used as a random value. That's one thing you can do with it. And it is generated in a distributed fashion so that nobody can cheat. And the nobody can cheat problem we're going to talk about extensively in terms of zero knowledge proofs. But the online portion of it is, once you get this so that it is both cheat proof and distributed, you can do things like store your public-private keys where no computer has the entire key because it's distributed and it's encrypted, and collectively these things work together. Now, random number generation is one piece. Another piece of this is at the point when we get done generating a distributed key, you can use that distributed key as a means to decrypt something. And the generation process requiring t out of n. So if you have n of 5, t is n over 5 is the 5 over 2 plus 1. So it would be 3. That's what I'm talking about distributed. It's got a threshold. Generally, that threshold is half of your total number of nodes plus 1. So if you have 101 nodes, then half of that is 50 plus 1 is 51 nodes that you have out there that would have to agree to do this. But since each one of them is working on an encrypted piece of data and using homomorphic encryption to do this, none of them have the solution until you get to that 51 point. At the point when you get the 51 that have the solution, and they share that, now suddenly all of them can say, yes, I can now, with this result from my distributed key generation, I can decrypt whatever piece of data I started out with, and my decrypted result can now be used in the future. And that is the basis for the Honey Badger distributed threshold systems. So when we look at this, we've got not just a signature scheme that we can build out of this, but we can also do Byzantine fault tolerance. Okay, it's got nice properties for that. It's also a distributed random number generator. So instead of having to have your network where all the people are computing everything all the time, in each round you can say, I'm going to generate in this round another random number, and from that random number I'm going to pick the nodes that are going to do the work, and that subset is going to do the calculation. So there's lots of applications for this. And when we get to the signature stuff, it doesn't require that we actually do the signature stuff unless we're going to be signing things. We can use just the threshold encryption before that for a lot of these applications. So there's a simple piece that's the threshold encryption. We're going to kind of walk through that, and we're going to talk about how that works. Now, remember my additive homophoric encryption, that means that I can take some value that I want to add, and I can actually encrypt the pieces of it, and I can work on the encrypted data and do the addition in the encrypted data, and when I get done, my decrypted solution from the encrypted data calculation is the same as my decrypted solution from the original data. That's what that means. That means that the nodes themselves don't have to have the decrypted data. All they have to do is be able to work on the encrypted data. An example of this is the Polyer that I talked about, but there are other systems out there of encryption that allow this to work together. So it's not that you have to use that. There are several of them. If you look for homomorphic encryption, you can see which ones allow this kind of an operation to take place. So we can start out having two values, A and B. We can encrypt those values, and then using this operation that we talked about on the encrypted data, we can take those two ciphertexts together, and we can, using those values, add them and encrypt the result, and later we can decrypt and get back our original correct result. So we're going to use that in a certain fashion to get our threshold encryption. Now, part of this system is, since we're starting out with an initialization on this homomorphic key, okay, we've got a setup phase. And in that setup phase, we're going to get two different pieces out of this. But now we're going to be dealing with two different kinds of keys here. Okay, and that's part of the confusion. There's this homomorphic key that we're going to be using, but our goal is to generate a new threshold ECDSA key, which is a different kind of key, but we're going to use the homomorphic in there to get to this point. So, threshold encryption, we're going to start out with our setup phase. And we're going to talk about the setup in terms of a couple things. The setup phase involves not just getting our process set up, but it also is going to involve a commitment that we're going to make. And the commitment is a zero knowledge proof. That if we have the commitment and the person used their key correctly, then later we can say, based on their commitment and their use of the key, even though I only have the encrypted result, later if you cheated and you didn't do your calculation right, I can mathematically prove that you didn't do your calculation correctly. So cheating in this system can be proven based on these set of commitments. So the first part of this is we've got to get stuff set up. And this is our homomorphic key that we have to get set up. So let me explain this in terms of a set of 4 people. And each one of these has a piece of what they need to have. And this is our first homomorphic key. So they've got a public and a share of the private key. They don't have the whole thing, but they're going to use this to set up their commitment scheme. And when we talk about commitment schemes, what we have to do is we got to get some idea of what a commitment scheme is. Okay? So, and this in and of itself has some uses that are really quite wonderful. The thing in Australia that I talked about last time, where they're doing the commitment to a particular kind of research, that's based on this commitment scheme. And in and of itself, this is a nice thing, because when you have a commitment scheme like this and somebody doesn't do what they're supposed to, later you can come back and say, no, you didn't match up with what you said you were going to do. but the Australian blockchain commitment scheme for biomedical research is definitely based on this. So we've got two different pieces here. We've got Alice and Carolyn, and Alice is the one that's going to make a commitment. Now, this can be understood fairly easily if you ignore the distributed nature and we just talk about here's how a commitment is done, and here's how we verify it at the end. Now, Carolyn can't know what the commitment is, but she can take the commitment and she can hold it, and at the end she can say, yes, you actually did commit to that. So Alice says, and this is based on just some coin flipping, so that you can just follow through with this. She's going to say, I'm going to do heads or tails, and here is my commitment. And so the easy way to look at this is that she says, in my commitment, I have taken one of these heads or tail choices and I have basically encrypted it. And here is my public key, but I'm not going to let you decrypt this until the end to see if I got the correct result. So Carolyn, here is my commitment, it's encrypted, and here is my public key. Okay? Then Carolyn sits there and she flips the coin and responds with, oh, hey Alice, the coin landed on tails. So she sends back, here's the result, I did the coin flip. Then Alice says, oh cool, I won. But how do you know she didn't cheat? Well, that's because before this she sent a commitment. Okay? Now she turns around and says, okay, I can now prove to you that I won because I can send you the information that allows you to verify the result based on the encrypted data that I already sent to you. And when I send back this encrypted result, okay, you can now check it and say, okay, you really did commit to tails, and when coin flip was tails, you really did win. So this is a commitment scheme. And the things to pick out of this commitment scheme is that, yes, there's some work on the committer's side and some encryption, but Carolyn only ever saw the public key, and that's the only thing she needs because this is kind of a signature system. And at the end, she uses the public key to verify the commitment, okay, matches with the tails that was what was flipped. So she doesn't ever have to know the private key information that was used to create the commitment. Now, the fact that Carolyn never has the private key means that she can't cheat either. She can't re-encrypt this to produce a new false commitment. The fact that she has the commitment means that she can check that Alice isn't lying. So here's the zero knowledge proof scheme in the commitment, where Carolyn can check it, but she can't see it, and Alice can make it, and she can't lie. So this is our commitment scheme that we're going to use.